Yeah, so we're going to be talking about standing waves for sound to begin with. Yeah, I'll do that pretty frequently. Thank you for the reminder. So when we're talking about standing waves, it's the same as it was before, especially when we're talking about standing waves in, say, a tube. However, when we were talking about a string, it wasn't quite clear. Sorry, when we were talking about a string, we knew what it meant for an end to be either fixed, meaning that the wave or that the displacement was 0 at that end, or free, meaning that the displacement was maximal at that end. We knew what those things meant because you could just either tie off a string on either end, or you could just let the string be like tied off to a ring on a pole and let that move up and down. For sound, it's not quite as obvious, so we need to figure out what those criteria refer to when we're talking about sound waves. So let me pull up a little animation or a simulation on my desktop. So it's going to stop me from sharing on this screen temporarily, but go ahead and look at the other screen. I think it's this one. Here we go. Hopefully you guys can see this. It's weird seeing myself share screen. Right, so above we have, at the top, we have an example of a sound wave that's, or a tube with air in it, that's open on both sides. And here we have a sound wave, sorry, a standing wave propagating in this tube. Now you might say, okay, well, what does it mean for there to be a standing wave if it's just like open, if it's just allowed to go in and out? Well, yeah, I can zoom in. Sorry, high resolution and all that. Better? So the point is remember that when by the way, when I say both sides are open, that does not mean that it's like free or fixed. It's just you just have a tube that's open on both sides. Think about a long steel pipe. Think about like hitting it with a mallet, right? It would produce a particular tone, and that's because a standing wave would form, even though you're able to have air go in and out of the tube. Similarly, we could have one side open and one side closed. This would be like a bottle that you're blowing in, like when you make the sound or whatever. Or you could have both sides closed, and that would just be like a solid, or not a solid, a hollow metal cylinder that you can whack on and it would produce a tone. Now, the question is which of these things correspond to a fixed end or a free end? It turns out that depending on what perspective you are looking at the sound wave, whether you're looking at it in terms of the average displacement of the particles or the pressure differential, it depends. So let's just real briefly, let's look at the both sides open really quick, and let's look at higher fundamentals. So right off the bat, we see that when both sides are open, if we look at the bottom graph, that is the divergence from average pressure, or the pressure differential. And you can see that like right now you have high pressure here, which is why it's high there. Right now you have high pressure here, which is why it's high there. And so what we see from this graph is that the pressure is always 0 on either end. Now you might say, why is that? And if you think about it enough, hopefully it would make sense. The air around us is always at atmospheric pressure. That's what it means, right? So the fact that, and this is a little bit of a complicated point, but it is true that atmospheric pressure is, or rather pressure in general, is a continuous variable. It tends to not change immediately, right? If you were to measure pressure at one place and then measure pressure at another place, the pressures would be pretty close if the 2 points were pretty close. It's continuous in the mathematical sense. So what that means is that the pressure, because the pressure outside the tube is atmospheric pressure, we would expect that the pressure right near the edges of the tube is also nearly at atmospheric pressure. And so this provides a constraint on the pressure values near the edge. It means that the pressure at either end of the tube, either end of the open tube, has to be exactly equal to atmospheric pressure. And hence, that would mean that this represents a fixed end standing wave because the pressure is fixed on either end. Now, we're typically going to be using pressure to talk about sound waves. However, you could also imagine what happens for the average displacement of particles. In that case, we would see that it is both ends are free. Notice that how both ends are allowed to oscillate freely. And that's just because the air molecules can go in and out, and that's not surprising. However, do note that when you say one end is fixed, that means something only for a particular type of wave or a particular description of the wave. If you're instead talking about, say, average displacement, if you were talking about average displacement and you said that one end or both ends were fixed, that would mean for pressure that both ends are free and vice versa. And we can look at higher and higher harmonics, or overtones as they're called in this animation. And we can also look at what happens when you have both sides closed or both sides open. A link to this will be in the lecture notes, or at least the URL will, and then you can type it in. So check it out if you're interested. But we're going to go back to the lecture notes, just so that I can kind of give a summary of what we see in this sort of animation. Share screen. Excellent. That worked a lot better because it means that I don't have to worry about my tablet crashing. Right, so what we learned from that animation is that when we say a pipe or a tube is open to the atmosphere, that means that that side is fixed for pressure, right? And we're almost always going to talk about pressure when we use the pressure description when we talk about standing waves for sound, or just sound waves in general. So I will leave that as it is. Now, I mentioned why that's the case, but what it boils down to is that either end has to be at 1 atmosphere, because if it's not, then the air immediately surrounding it would push on it until it was. And so what we see is that we see oscillating pressure, oscillating pressure waves inside this tube that has 2 open ends. Now, just as a reminder, pressure leads displacement. That's an H. Meaning that if the pressure wave is at a peak, the displacement wave will be at a equilibrium, and then a few fractions of a second later, when the pressure wave is at an equilibrium, it goes up and then it comes back down, then the pressure or the displacement wave will be at a peak. So it follows it by 1/4 of a wavelength effectively, or equivalently by pi/2 radians. So what that means is, remember that a fixed end means that there's no displacement or no oscillation at that end. And so if the pressure leads displacement by pi/2, that means that when the pressure is at 0, that means that the displacement is not at 0, it's at its maximum or its minimum, which means that open to the atmosphere also means it is a free end for displacement. And that's just because of this fact that the pressure leads the displacement by pi/2. So you can translate a fixed end to a free end and vice versa if you shift your wave over by pi/2 radians. and this view is kind of intuitive too, right? Because the molecules themselves are free to move in and out of the tube because there's nothing blocking them. So of course they'll be allowed to move. Now we also saw in the animation that if I am talking about a tube that's closed to the atmosphere, ATM is the abbreviation, that means that it's a fixed wave for displacement. And again, that's not surprising. The particles can't move in and out of the tube. They're just stuck there on the edge. So what does that mean for pressure? Pressure leads displacement. And so again, it leads displacement by pi over 2 radians. And so when the displacement is at equilibrium, the pressure will be at a minimum or a maximum. So that tells us that if a tube is closed to the atmosphere, that means that it's a free end for pressure. So it's just important to keep these straight, but hopefully you understand the reasoning so you can think it through yourselves. The idea is just that if the tube is closed, say on either end, then there's nothing stopping the pressure from being whatever it wants to be at the end, right? There's no outside pressure making the inside pressure conform. There's a barrier there preventing the outside pressure from affecting the inside pressure. So everything else is the same though, right? Once you have what it means for an end to be fixed or free, you can actually then just say, okay, now that we know what the boundary conditions are, now we can go and we can look, using our equation or just thinking through the problem, we can think about what types of fundamentals and what types of harmonics can form in that tube, whether it has both ends open or both ends closed, or one end open and one end closed. By the way, for a flute, for example, a flute has 2 ends closed, except it has little holes that air can go in and out of. So those little holes do not affect the standing wave. They just are basically a way for the sound to go in or out. So a flute is a very good and easy example of a thing that you can just calculate using the formulas that we know. It has both ends closed, so if we were talking about pressure waves, we would go say that it has 2 free ends, and so then you could go plug in your formula, you get that lambda n is 2L over n, where L is the length of the flute, and you could go and you could calculate the actual frequencies that the flute can produce. And by the way, covering up these holes, actually, I should rephrase. I don't know a whole lot about music, but I suspect that by covering up various holes, you're making the tube either fixed or free at different lengths, and that affects the harmonics that can be produced. Or, sorry, that affects the fundamental frequency because you're effectively shortening or lengthening the tube. But I don't actually know exactly how, like, the fancy modern flutes work, because I know that sometimes the buttons go up and sometimes down. Anyway, feel free to look it up. The principle of trombones. Yeah, no, I believe that. Right, so let's talk about one-dimensional phase differences now. So that's enough with standing waves. Standing waves are great, but there's a lot more that goes on, especially with regards to sound. So let's change gears. So we're going to need to talk about, in order to talk about multiple dimensional interference, like this is what happens when you have 2 speakers in a room and you're wondering where are the dead zones and where are the loud zones. Perhaps it seems counterintuitive, but you actually need to fully understand how phase differences work in one dimension in order to understand that problem. So what we're basically trying to do is we want to model what happens when there are 2 speakers. We want to know where there's constructive or destructive interference. And hopefully by the end of today, we will be able to answer that question. That is, where are the dead zones? And this is something that a sound engineer would actually be interested in knowing about. By the way, just a quick anecdote. A few years back, I was in Florida with my wife. well, with my now wife anyway. And we were staying at like a hotel, and the lobby for the hotel was interestingly shaped in that if you stood in a very particular part of the room, you could hear everything that was said in the lobby. And this was both a combination of interference effects and optics, which we'll get to later in the quarter. But it's an interesting effect, and that's the kind of thing that with the right architecture you can design for. Like I could hear a pin dropping on the other side of the room, but if you move over just a few feet, you can't hear that anymore. So this is definitely something that happens in real life. So if we want to answer these questions, we need to talk about where and when constructive or destructive interference occurs. It is the case that the only way to get constructive or destructive interference is for the humps. I'm going to put the humps. By the way, I'm going to be using the word humps to refer to peaks and troughs just because it's like two humps. We want them to match up. If they match up but are opposite, then you get destructive interference. If they match up but are in the same direction, you get constructive interference. So for the sake of the calculations that we're going to do, or for the sake of, yeah, for the sake of what we're going to start out with, we're going to assume the following. Assume we have equal wavelength, period, and direction. So all we're just going to do is we're going to analyze, or try to understand better, rather, when we get those types of interference. To do so, we're going to consider the overall phases. Now, remember when we talked about wave functions for the first time, harmonic waves? I defined this thing capital Phi. Capital Phi is the total phase, or the overall phase, and it's just 2 pi x over lambda plus 2 pi t over t plus little phi plus the phase constant. That just tells you where in the cycle you are. If you are if capital Phi, for example, equals 2 pi, that means that you are at the beginning of your cycle. If it's a cosine wave, you're at a peak. If it's a sine wave, you're at a trough. Sorry, if it's a sine wave, you're at equilibrium. If you were at pi over 2 and it's a cosine wave, then you were at equilibrium, and so on. Basically, this is the thing that tells you where you are at in your cycle. And so remember that all we need to do to figure out where we are, all we need to do to figure out what the relative position is of the humps in these two waves is to consider what the difference is between their two phases. If their two phases perfectly overlap, if the difference is 0, then you would get constructive interference. And if their difference was pi, you would get destructive interference. So we're going to simplify this problem of two speakers in a two-dimensional room. We're going to simplify the problem and consider one-dimensional waves. We'll get how this relates back to two-dimensional waves or sound waves in a room later, but we certainly need to understand how this works for one-dimensional waves. So in doing so, we just compute delta phi. This is just the total phase of wave 2 minus the total phase of wave 1. And by the way, it doesn't matter if they were both sines or both cosines, they just have to both be the same type of thing. And we have to assume that they have the same wavelength, period, and direction as well. So maybe they're both traveling to the right, for example, and maybe they all have the wavelength lambda, and they both have the wavelength, or the period t. So then we can just compute. So we already know the formula for phi for each of the waves. They have the same lambda, the same t. So this is 2 pi x2 over lambda. So x2 is the position that we're measuring the second wave at. That's the position that we're measuring the total phase of that wave at. one way to view this x2 is it's basically going to be the distance from the source of the wave to where we're measuring. And so if the sources are in different places, they might have different positions, even though we're measuring them at the same physical location. I'll explain this, or I'll draw a picture for this in a minute. So we have plus or minus 2 pi t2 over t plus phi 2. Now that t2 basically tells us how long since the source was turned on has it been running, or how long has it been since the source was turned on. So if the two speakers that we're imagining are turned on at different times, they will have different values, even though we're measuring their phases at the same instant in time. Minus 2 pi x1 over lambda, again, it's the same thing, but just a different position, x1 versus x2, and 2 pi t1 over t plus phi 1. And obviously they could have different initial phase constants. So doing some simplification, we get 2 pi x2 minus x1 over lambda, plus or minus 2 pi t2 minus t1 over t plus phi 2 minus phi 1. Or rewriting one more time, 2 pi delta x over lambda plus or minus 2 pi delta t over t plus delta phi. So the idea here is delta x just tells you the relative position of the two speakers. If one speaker is 2 centimeters behind the other speaker, then delta x would be 2 centimeters. If one of the speakers was turned on 5 seconds after the other speaker, then delta t would be 5 seconds. And if they started out of phase, then you would have to account for that difference in phase constant in delta phi. So how do we translate this delta capital phi, this difference in total phase, to interference? Remember, all this delta phi tells us is where in the overall cycle the two waves are. It tells us rather how far away from each other the two waves are in their relative cycles. So if, say, the first wave had a total phase of pi and the second wave had a total phase of 0, that would mean that they're precisely pi, or half a wavelength, out of phase at that moment in time and at that position. What would that mean? It would mean that there'd be destructive interference, and it would have a phase difference of pi. Similarly, let's say that one of them had a total phase of 2 pi, the other had a total phase of 0. Again, the difference would be 2 pi, but keep in mind, if your total phase is at 2 pi, that's the same as being the total phase of 0. And so they would have the same total phase, so they'd be perfectly overlapping. That would mean that they would be totally in phase, and thus produce constructive interference. So, and again, I'm going to be drawing pictures of this in a minute, but I need to get the math out of the way, because it'll be easier to draw it once we can add some simplifying assumptions. So the way this happens is that if we get delta phi is equal to pi, or 3 pi, or 5 pi, etc., it could also be negative, then we get destructive interference. If we have delta phi is 0, or 2 pi, or 4 pi, etc., that gives us constructive interference. And you guys hopefully see the pattern there. If you have an odd multiple of pi, then you get destructive interference, and that's because cycles repeat on even multiples of pi. So if you go an even multiple of pi plus half of a half of a full cycle, then the two waves would be out of phase. If it's neither of those, then we get some sort of in-between interference. You don't get fully constructive, you don't get fully destructive. Maybe the sum of the two waves would be slightly smaller than the sum of their amplitudes, or maybe it'd be slightly larger. We don't really have a name. Maybe you call it partially constructive or partially destructive. So how do we get these, like what can we do to our sources in order to get those phase differences? Well, there's a few different ways that you could arrange your speakers or arrange your setup to get these different phase differences. One way is that they could travel different distances to get to the same destination. I cannot spell today. So one example of this would be two speakers at different places in a room. If you're looking at a particular place in the room, the speakers will have traveled different distances to get there. So that would be like delta x. They could also have traveled for different duration. Meaning that you turn them on at different times. Alternatively, they could have started out of phase to begin with. Or it could be all three of these. Right, basically, I was just describing what each of these variables represent, delta x, delta t, and delta phi. And it could be, you could combine any three of those variables in order to see what the result is when you interfere the two waves. So let's look at each of these three cases separately. So we're going to have two speakers, and I'm going to list some assumptions for our first set of speakers, for our first example. So the speaker assumptions for our first example are the following. We will assume that the speakers start in phase. One way to ensure this in the real world, by the way, would be have them connected to the same wire so that they're receiving the same signal, which means that one wouldn't be a cosine and the other's a sine. They would have the same input, meaning they would start at the same phase. So what does that imply? That implies that delta phi is 0. We could also have them turned on at the same time. That would mean that delta t is 0. So what we're doing is we're basically turning off two of our variables, and we're going to look at how one of our variables affects the interference. And we're going to have them be offset from each other. Delta x by that much. Now keep in mind that this is, we're strictly talking about one-dimensional waves here. So what we're really doing is we're going to have two speakers which are like lined up with each other and offset by different distances. So here's a picture. You have one speaker. It's so hard to draw these things sometimes. One speaker here, and it's producing some sound wave. Say it's like this. And then we have the same speaker, but offset by a small distance. Let's say like there. And so this distance here would be delta x. If we looked at a given point in space, the distance that each wave will have traveled is different, right? And so that's what so that's why that delta x tells us, oops, oh boy. I don't want to redraw it because it won't look right. There we go. So what can we see from this particular example? Well, in this case, what is delta x actually equal to? I shifted it over precisely 1/2 of a wavelength. The wavelength is, say, this distance to this distance. I shifted it over half that much. So in this case, if delta x is equal to lambda over 2, well, you can see what happens when this happens. You have a peak here and a trough here, and so when they overlap, you'll get 0. That's destructive interference. So if delta x is lambda over 2, half a wavelength, then you get destructive interference. Why is that mathematically true? Well, delta phi is equal to 2 pi delta x over lambda. So if we plug in delta x as lambda over 2, that's equal to 2 pi delta x over lambda, which is 2 pi times 1/2, which is just pi. And if we go and we look up at our criteria here, we see that, well, when delta phi is equal to pi, you get destructive interference. By the way, maybe I'll just back up here. The reason for this is that sine of, say, x plus pi plus sine of x equals 0. And similarly, sine of x plus 2 pi plus sine of x is equal to 2, and so on. So you can just test this out by just taking a wave that's sine or cosine of x plus whatever your phase difference is, and add it to just sine or cosine of just x. And that will tell you whether or not you get constructive or destructive interference. All right, let's do another set of speaker assumptions. This time, we're going to have them be in the same place. But we're going to have them have different turn-on times. So here we're going to have delta x is 0. That means that they start off in the same place. We're going to have delta phi is 0, meaning they have the same input signal, but we're going to have delta t is not 0. And this one's always the hardest to draw, so bear with me. So basically, everything is identical. Everything about the speakers are identical, except one speaker is turned on late. So let me draw a picture. So say this is at, so let's say, just for the sake of argument, let's say that t equals t over 2 is when speaker 1 turns on. And t equals 0 is when speaker 2 turns on. This is just for the sake of example. So here's speaker 1. It just turned on at this moment. So this is t equals t over 2 that I'm drawing here. This is when, this is right when speaker 1 turns on, but speaker 2 has already been on for half a period. So it should have spat out a wave that was half a period long, right? Okay, now what about at t equals capital T, after one full period has elapsed? What would the waves look like then? Well, let's find out. So we know that at t equals capital T, speaker 1 has been on for half a period. So it should look exactly the same as speaker 2 did after half a period. But speaker 2 has now been on for a full period. And so the part of the wave that was present after half a period should have moved over and had another half of a period come out, right? So now what we see is that we have destructive interference here. So this is has a half period head start. By the way, for the record, this horizontal axis is x in both cases. Just to clear things up a little bit. That's why it traveled a distance. So what we learned from this example is that if delta t is equal to half a period, i.e. if one turns on half a period later, we get destructive interference. And the mathematical reason for why is the same reason that we saw for half a wavelength out of phase. Capital delta phi, which is plus or minus 2 pi delta t over capital T. This is just plus or minus 2 pi times a half, which is just plus or minus pi. And again, we go back and we look up, well, our criteria for destructive interference is that the total phase differed by pi or 3 pi or 5 pi, so we get destructive interference here. In fact, what we're actually doing is we're demonstrating why this criteria is true in the first place by looking at each of these examples. So now we're going to do the same thing. We're just going to now just look at the third variable. Here we have delta x is 0, delta t is 0, but we're going to have delta phi not be 0. And so this is exactly the same as before, i.e. when we were first studying constructive or destructive interference, we just had two identical waves, but one was shifted relative to the other. And that's all this does. this just tells us where our waves start. So the picture might be the following. Let's say you have a speaker here, starts out, it's just a normal sine wave, say. The second speaker should be out of phase. Let's say delta phi is pi, out of phase by pi, meaning that the second speaker should be either pi ahead or pi behind the first speaker. That just means that instead of going to, it basically just means we take what would have been over here and we shift it over to the left or to the right. It doesn't matter which one. Regardless, the picture ends up looking like this. And so, again, we get destructive interference. And that's not surprising. That's just because delta phi, when delta x and delta t are 0, is just little delta phi. And so if it's pi, then it's pi, and so you get destructive interference. So those are the 3 different variables, and obviously you can combine them in different ways. And if we had chosen delta x, delta t, and delta phi to be different things, then we would have gotten a different type of interference, either constructive or not any particular type, just partial interference, depending on what the variables are. But I'm going to give you just a quick note, because this whole time difference business is can be a little bit confusing. So instead of talking about time differences, all we're going to do is we're just going to adjust what each wave's t equals 0 to means, so that we can absorb. So we're adjusting what we mean by t equals 0, so that 2 pi delta t over capital T just becomes a phase difference. So this basically lets us just discuss delta x and delta t. The reason why we can do this is because if you wait long enough, it doesn't really matter whether your wave has, how long your wave has been on. It just matters where in the cycle it is, because the only difference between these 2 pictures is that very, very briefly, there is a place where in the first picture, there's no second thing to interfere with. But as long as you wait long enough, both waves will be present at any given position. And so we could just say that this wave is just shifted forward by a phase of pi. And so we can absorb that that delta t is equal to capital T over 2 and just call it, oh, well, the phase difference is just pi more than we had originally thought. So it's just a simplifying assumption. It makes it easier to handle these things, especially because sound travels really fast. So in general, when we're talking about 2 waves interfering, we're talking about those 2 waves actually being present at the same place. But because sound travels so fast, even if there was a slight delay in turning one on as opposed to the other, they will, given a very short amount of time, they'll both be present at that location. So what we can do is we can just eliminate this need to talk about delta t and instead just talk about what is the relative phase differences. This is basically what is the value, what is the value of the speaker at t equals 0 and x equals 0, and where are those speakers projecting sound to. So we'll get to that in a minute. We'll get to how this relates to 2-dimensional or 3-dimensional waves, but while we're here, we may as well continue talking about 1-dimensional waves and their interference in a slightly more general setting. So we're going to talk about beats, or beating waves or beat frequencies. So the phenomenon of beats occurs or arises when we ask the question, what if the waves aren't exactly identical? So in the past, when we were talking about interference, we assumed that they had the same, where was this? We assumed that they had the same wavelength, the same period and the same direction. But what if they don't? What if their wavelength is a little bit different or their period is a little bit different? We still have to assume they have the same wave speed. That's certainly true. But when the frequencies or the periods are slightly different, we get an interesting phenomenon. That phenomenon is called beats. So I'm going to draw another, this is an exaggerated picture, but I'm going to draw a picture nonetheless. Here's one speaker. So let's say this first speaker has a frequency like this. Let me make it a little bit smaller. Something like that. And let's say that we have a second speaker producing the same amplitude, same wave speed, but different frequency. That goes something like this. So here we have the amplitude and wave speed and direction are the same. But frequencies are different. So what happens if we were to overlap these two waves? Well, we see that the trough there aligns with the trough there. So we would have constructive interference here. The two waves would add together and you'd have a larger trough. I drew this poorly. That's a bummer. So I don't want one to be a multiple of the other. It's hard to get right. Let me move where the constructive interference is occurring. There we go. It's not perfect, but you guys can get the idea that we would have constructive interference here, and we would have destructive interference here. Because the frequencies are different, occasionally, by the way, this is a plot in time now. We're looking at a fixed location. We're just seeing what happens to the, and the way we can see this is that we're looking at how their frequencies differ, so we should see that we have the oscillation rate changes with time, or the oscillation rate in time are different between the two waves. But what we can see here is that if you're at a fixed location, sometimes you'll have constructive interference. The two waves will overlap and you'll get a larger amplitude, and sometimes you'll have destructive interference. The waves will overlap and you'll have zero amplitude. So what's the resulting observed phenomenon? We would get that sitting at one place, because this phenomenon occurs when you're looking at a fixed location, you'll have changes in time. There will be an oscillating volume. So this is similar to the principle of having two waves at different places, and you have two places that have different volumes. Here we have two waves at the same place but different frequencies, and now you have different times with different volumes. This interference effect, and by the way, the reason we have oscillating volume is because you'd have more volume when they are constructively interfering and less volume when they destructively interfere. So it is caused by interference. And it is called, this phenomenon is called beats, or they are called beats. So let me pull up another website so I can show you this phenomenon. So I'm going to pull it up on my other. And hopefully you will be able to hear this. Sound on. Let me zoom in a little bit. If you can't hear it, I have another one. But so let's just take a look at what happens. So we can adjust the frequency of the blue wave. Oh, it's very laggy. I'll do it slowly. We could adjust the frequency of the red wave independently of each other. And so what we'll do is we will see how these two waves affect each other when they overlap. So let me make the frequency difference like, let's make one 250. And let's make the other, say, 270 or 300. So what we see is that in this region, at the bottom, this is the overlap of the two waves. We see that we have some places where the amplitude is higher. That would mean that we would experience louder sounds, and some places where the amplitude is smaller, we would experience quieter sounds. And so we could actually go and we could figure out how long does it take for this process to repeat itself. It looks like it takes exactly 0.02 seconds. Now, 0.02 seconds, that would be the period associated with a frequency of 50 hertz. Now, if you go and you look at the formula or the numbers that I plugged in, they have a difference of 50 hertz. So perhaps those two things are related, and indeed they are, and we'll get into the mathematics of that in a minute. But I just want to have you guys be able to listen to this. So I don't know if you'll be able to hear this. Headphone warning. I don't know how loud this is going to be. But you should be able to hear this phenomenon. I might have to share computer sound. Here we go. Did you guys hear that? No, okay. Oh, there it is. All right. So hopefully you guys managed to experience beat frequencies, and it should have been like a so that wasn't like something weird going on with your headphones or some feedback from the computer. It was actually what was happening. You were hearing a 500 hertz sound in one ear or from your speaker and a 503 hertz sound from the same speaker, and so those interfere because of this let me share my screen again, because of this beating phenomenon, that sometimes they constructively interfere and sometimes they destructively interfere. And so when they constructively interfere, you get louder sounds, you get the louder part, and when they destructively interfere, you get the quieter part. And that happens at a particular rate. The audio's laggy. Is it? Let me try something else. Testing, 2, 3, better. Still worse. That's weird. How about now? I wonder if it's, oh, it is because my tablet is running out of system resources, whatever that means. I mean, I know what that means, but it's because my tablet's slowing down. I promise it's not my, promise it's not my sound, not that. It says low system resources. Let me close out of my browser. Yeah, that's what I just did. Chrome is gnarly in that regard. All right, so is it better now? So it should be okay. Try closing some applications. Stop it. Okay, good now? Perfect. Okay, excellent. Thank you guys. Right. Right, so what we just experienced was something called beats. Now, let's try to understand why that happens. And we can understand this mathematically. So if we take a look at our first function, say, our first wave function, again, we're looking at it at a fixed place, so let's just call that fixed place 0. Let's call it 0 of t. We're going to examine at x equals 0. That's without loss of generality. You could just plug in whatever number you wanted for x, but we're just going to plug in 0 because it makes the calculations easier. So then our wave function looks like a times cosine of 2 pi t over t1, because they have different periods now, plus phi 1. And our second wave function at the same location and time would look like a cosine of 2 pi t over t2 plus phi 2. Now, one thing that we can do is, without loss of generality, we can set phi 1 equal to phi 2. So all phi 1 and phi 2 do is it'll just, their relative values will just change when the first loud part happens. But we're not interested in when that happens, we're just interested in what frequency does it get loud and quiet again. And so basically, those phase constants don't matter at all. It'll just affect where you start, but it won't affect the actual phenomenon of beats. So that means that the sum of these two waves, f of t, is f1 of 0 and t plus f2. That's how interference works. Remember, you just add up the waves of 0 and t. That's just a times cosine of 2 pi t over t1 plus cosine of 2 pi t over t2. Or rewriting it is a times cosine of 2 pi f1 t plus cosine of 2 pi f2 t. Remember, 1 over t is equal to f. So you can use some trig identities, which I'm not going to show you. Feel free to derive it yourself if you're curious, to get that the end result of f of t is 2 times a of 2 pi times f1 minus f2 divided by 2 times t. Sorry, I'm missing a cosine. Let me move this. 2 times a, 2a times cosine of that times cosine of, these brackets again, of 2 pi times f1 plus f2 divided by 2 times t. So this just comes from a trig identity. It's just a sum of two trig values, or it's the sum of cosines identity. And so we could plot this particular function with respect to time. It's relatively easy to do, but it's going to come out looking poorly, I promise. And so what I just drew is not actually the wave. The wave would look like this. So what I drew was the envelope to the wave. And you have the other side of the envelope too. For relatively obvious reasons. So what are these, how can we interpret this formula? Like, how can we use this to understand what we're hearing? Well, for f1 equals f2 plus some small delta f, that is, the first frequency and the second frequency differ by a small amount, that means that 2a times cosine of pi delta f times t, that is just that term, this varies slowly. So what I'm looking at is I'm just looking at this first term. So if we plug in f1 minus f2 is equal to delta f, then we just get, for that first part, it's not like they're not added together, I'm just looking at the coefficient. You get 2a times cosine of pi delta f times t. And if delta f is small, well, the way to interpret this then is that the period is very long. And so, in fact, we can hear this. So normal sound waves are 20 to 50 to 1,000 to 20,000 hertz, meaning that they oscillate hundreds of times per second. But if the sound was oscillating sufficiently slowly, we would just hear its volume changing with time. You'll notice, by the way, if you play a sound and you can adjust the frequency, if you play a sound lower than like 20 or 30 hertz, it starts to just sound like clicks rather than a very low tone. And that's the same phenomenon. You're just hearing the individual pulses as individual things rather than as one continuous tone. And so what we can view this as, this term, we can view it as a time-dependent amplitude. So what's really happening is by causing these two waves to interfere with each other, we can instead view it as the two waves coming together, but their amplitude now varies with time. And the last term, the cosine of 2 pi times f1 plus f2 divided by 2, this would be large, potentially, depending on the original frequencies of the original waves. This would be the sound that we hear, or the tone that we hear. We hear the average of the two frequencies. So what it looks like is that f of t looks like a of t times cosine of 2 pi times f1 plus f2 divided by 2 times t. And so this would have this wave, we would hear that wave on our ear oscillating, or rather we would hear it as if it were just a sound wave on our ear. Where'd my plug go? With a frequency of f1 plus f2 divided by 2, which is precisely the average. And so that's the tone that we hear, but the amplitude tells us how quickly the volume is changing. And that depends on the difference in the frequencies. So what we find, and let me turn to the next page of my notes, or I suppose what we learn is that the beat frequency this is a definition, is given by delta f. And the carrier wave frequency is given by f carrier equals, it's given by the average over 2. And so there is a little bit of a point to be made here that you might say, oh, well, why is it that the beat frequency, usually when we talk about something having a frequency f, usually it's because it comes next to a 2 pi times t, and then you have an f here. So why is it that the beat frequency is delta f instead of delta f, say, divided by 2, so to cancel out the 2 from the pi? Well, it turns out that the beat frequency isn't necessarily the frequency of a wave. It's the rate at which the amplitude changes. But the way that we detect sound is not, or the way that we detect volume changes is not the value of the amplitude, but it's the absolute value of the amplitude. So what's happening here is that the amplitude goes from positive to negative over the course of 1 divided by delta f. That's why there's a single pi instead of a 2 pi. And so so the point is that what am I trying to say? One period is precisely this long. And we hear that because we hear the absolute value rather than the amplitude. So basically, this delta f is just how long between loud parts. And a loud part is, those 2 points are both loud parts. So this would be, or this would be t, a beat, 1 beat period. Right, so that's a convenient aside, but beats are super interesting, and it's actually how you tune a guitar, right? We have time. I can go do a demo. I'll be right back. I'm gonna go grab my guitar. All right, so this is a better guitar for demonstrating beats. So let's see if I can demonstrate. So one way that you might tune a guitar is, so let's zoom in on this, is you fix one of your notes, say the E string. Let's say you know the E string's in tune. How do you tune the next string? Well, the way you might do it is you know that various frets correspond to various notes on one string might correspond to various notes on another string. One way to check that is to just play two notes that should be the same on different strings, and if you hear a beat, that means that the frequency that's coming out is different. So I'm actually going to use what are called harmonics, and it's actually precisely as it sounds. So the 5th fret here produces a very clean harmonic. The reason for that is that that would be precisely 1/4 of the length of the string. And so what standing wave would form when you have 1/4 of a wavelength fixed? So by putting my finger on the fret, I'm not pushing down, I'm just lightly tapping it, I'm making a node appear there. So let me draw a picture. So we have our guitar. That's a terrible, how do you draw a guitar? And then it's like, something like that. So we have our guitar, we have our strings, right? So the string is fixed on both ends, and I'm putting my finger very lightly there on the 5th fret, which is precisely 1/4 of the length. So that means if we were to plot the wave that comes off, if this is L, we know that, and this is 0, we know that there has to be a node there. So that means that our wave has to be which harmonic? It should be the fourth harmonic, right? So this is the 4th harmonic of the fundamental of that string. Should be exactly 4 times higher, by the way, or 4 times the frequency, which should be 2 octaves higher. Sorry, 4 octaves higher. No, 2 octaves higher. That's music business, not physics. Right, so I produce that standing wave, right? Makes a nice, clear tone. Now, I just need to figure out what is another tone that I can produce on a different string that should be the same, but if the two strings were out of tune, if they were not tuned correctly, they would produce a beat frequency because their frequencies would be different. Well, I can look at another string, and it happens to be the case that in the standard guitar tuning, if you look at this is the 1st string, the 2nd string, this one, so this string here rather than this string, the 2nd string, if I put my finger precisely 1/3 of the way up the string, I will get a different harmonic. That would be the 3rd harmonic, but because the string is under more tension and it's also a lighter weight string, the wave speed is different, so we'll get a different frequency. It turns out that those two frequencies should be identical. That's just the way guitar is standardly tuned. So here's the 1st frequency. Here's the 2nd frequency. So it's clearly not in tune. And actually, if you listen closely, you can actually hear a little bit of wobbling or beating. And so watch what happens as I adjust the tuning. So now, the wobbling still happens if you listen very closely, but it's a lot slower. Why does that happen? Well, let's look at the beat frequency. The beat frequency is the difference between the two frequencies of the waves. So as the frequencies get closer together, that means that the beat frequency goes down, which means that there's a longer time period between peaks. So if the frequencies get closer and closer, eventually, the volume won't change at all. And all I'm doing, by the way, by changing these pegs up here, is I'm adjusting the tension, which changes the wave speed and hence the frequency. And now, these two strings are in tune with each other. That doesn't mean that the top string wasn't tuned to begin with. It's probably out of tune. But now, they will at least sound okay together, rather than being clearly out of tune like those two are. You can hear the beating occurring there for those same harmonics. Right. So, in fact, before I even knew any of this, when I was taking guitar lessons as a teenager, I had never taken a physics class before. I didn't know about beating, but this is what my guitar teacher, who also had no physics training at all, taught me how to tune a guitar. So it is a useful phenomenon. You can tune a guitar by ear using this this beat technique. As long as you can tune one of your strings, you can tune all of them. Oh, that's really out of tune. I should tune the rest of it later. Right, I'm gonna go put this down really quick, and then we can get back to lecture. So it's a nifty application, at least in my opinion, of beat frequencies. By the way, the reason why we use harmonics, we're talking about, like when I say harmonics, I mean the harmonics on the guitar, lightly putting your finger in one place, is because the way a guitar string works, when you pluck it, it doesn't, how do I want to phrase this? It doesn't produce very clean tones, and what I mean by that is that the Fourier decomposition of the sound wave that it produces when it oscillates is very messy. There's a lot of higher overtones, and that's part of what gives a guitar the sound a guitar has. But by pinching the string in a very particular spot, what you're doing is you're basically eliminating all the overtones except a particular one. And that's why you can get a nice, clean, almost perfect sine wave out of a guitar by using those harmonics. And the reason we want to eliminate all the overtones is that way then we can isolate just one frequency on each string, so then we can do this beat comparison that we can use to tune the other strings. Right, so I promised this, and now is the time to do so. Let's talk about interference in higher dimensions. Hopefully you guys are able to hear that beat frequency on the guitar, by the way. I haven't done that demo ever on a video, so, but it good. That's good. Right, so we're going to talk about higher dimensional interference. This whole idea of talking about interference in one dimension was just a way to segue to understand, you know, where is a loud region, or where is that part in a room where you can hear even the smallest whisper, right? So what we do is, well, let me draw a picture actually. Let's say this is a room, square room. Obviously rooms are more complicated because they're three-dimensional, but let's just assume it's a square room. Let's say we have speaker 1 here, speaker 2 here. They're both connected to the same wire, meaning that they should have the same phase. They're both turned on at the same time, so they have the same starting time. The delta t and delta phi are both 0 for any given point in space. The only thing that might be different, say we're interested in what happens at this point x, would be the distance from the speaker to the point that we're interested in. You just mark it with an X. Those distances could be different. So the distances are possibly different. Possibly different. So we can use these to determine the phase differences. Right, remember that the phase difference between two waves at a given, the phase difference is just based off of how far they've traveled, how long they've been on, and what their initial phase is. In this case, it doesn't matter that they're traveling in different directions, because we can still measure the distance from the two speakers to the point of interest. And if, for example, they've traveled the same distance, and they've been on for the same duration, and they have the same time constant or phase constant, then the pressure, perhaps the pressure is high at one point in time for both of those, then the pressure will add up. You'll have double the amplitude. Right, we have to assume that the amplitudes are the same. So typically you'll want to assume that x1 and x2 are close to each other. But you're right, in real life, where we have to deal with the fact that the amplitudes differ, you could get different amplitudes. However, the difference in amplitude won't affect whether you have constructive or destructive interference. All that means is that rather than having the amplitude double or just go to 0, when you have constructive or destructive interference respectively, you'll just have the sum of the amplitudes and the difference of the amplitudes at those points where you would have constructive and destructive interference respectively. And remember that the phase difference tells us the interference type. So let me show you a picture of just the kind of thing that you can do. Or not a picture, an animation, I suppose. I don't want that open. Share screen. Right, this is a nifty website. I can zoom in again, or no, I'm already zoomed in. So what we have is we have two speakers. We have a speaker on the right and a speaker on the left. They're both producing sound with the same wavelength. You can tell it's the same wavelength because the distances between peaks and troughs are the same. And they have the, oh, you can't hear. Why is this happening? I know what's happening. I want to not view the screen. Okay, how about this? I have an idea.
Can you hear me now? Oh God, that's horrible and laggy. Can you hear me all right? Okay, so I'm just gonna use my headset until I have to switch back to my normal tablet. Right, so the wavelengths are the same. Just look at the distance between peaks and our troughs. It doesn't really matter. The frequencies are the same because they're emitting a pulse at the same time. And at a given position in space, the waves will have traveled a different distance, right? So let's just look in a straight line path. So let's just look, say, here. So, and let's change the distance. So have 4 centimeters. The sources are 10 centimeters apart. So the difference between the sources is 2.5 times larger than one wavelength. So we saw before that if the difference in position, by the way, we're just looking at this point along the axis. If the difference in position lines up or is an odd multiple of half of a wavelength, 3 halves of a wavelength, 5 halves of a wavelength, and so on, then you would get destructive interference. This is because the phase difference would be an odd multiple of pi. So what we see is because the sources are two interference along both lines. Now, what we can, and that's just because one will have always traveled 2.5 wavelengths further than the other. Now let's check. We will have constructive interference between them because they're exactly 2 wavelengths apart. So even though one will have traveled 2 wavelengths further, you can see the left one overlaps with the black on the right one, and you always get constructive interference along these lines. Now, we can get neither constructive nor destructive because the peaks of one don't, blue and red lines, those are the lines of destructive and constructive hyperbolas. I believe those are hyperbolas. Yeah, they're probably hyperbolas. Point being that there are very interfered. Notice how these 2 lines, the black lines, by changing the distance between them at various points in this room, you would get loud areas along these red lines have destructive interference because the gray and the black are overlapping there. And then in other areas, you'll just have something else. Rounding. So you can actually even see delta S, which is if you just divided it by lambda, would give you the fraction of a, would tell you how many pi's they're out of phase by. Here, destructive interference, they're out of phase by 1.5 pi's, 3 halves pi. Sorry, they're out of phase by 1.5, 2 pi's. So that's 3 pi is their total phase difference. Here, their path length differs by 1 2 pi, which is just 2 pi. And so you can just move your mouse around, and you can see where their phases differ. And so you would get a similar effect. It would just be a more complicated shape. I could put this in slow motion if you wanted, but I don't know how useful that is. So let's get back to the lecture. So I'm going to stop sharing here, start sharing here, unmute there, take off headset.
Is the audio okay? Okay, right. So there is possibly a slight paradox that arises from this type of problem. And that's the question of where or how many of these quiet spots do you have for every loud spot, or vice versa. And we can approach that paradox by talking about wave energy and interference. So it turns out that there is no arrangement of speakers such that they destructively interfere everywhere. What I mean by this is in 2D or 3D spaces for separated sources. What I mean by that is that there's no arrangement of however many speakers that you want in a room, such that at every place in that room, you hear nothing. And that kind of makes sense, right? Because we know that total energy is conserved. we know that total energy is conserved in general. And so if we had 0 sound everywhere in a room, then there'd be no sonic energy there. We know that at places where the oscillation is 0, there's no energy associated at that location. And if it was 0 oscillation, 0 destructive interference everywhere, you would have 0 energy. However, each speaker is outputting energy. They're not outputting a negative energy. So the total energy in the system should be the sum of the energy of each of the speakers. So what we get is that for each region with destructive interference, we also have a region with constructive interference. And that's only true for 2 speaker systems, by the way. Because say you had 3 speakers, then you could have 2 destructive interference regions for every 1 constructive interference region. And that's just because the constructive interference region would have 3 times the energy of just one of the speakers, so you can concentrate that. So basically what we can do with speakers is we can concentrate where that energy goes. And in fact, we see that, we'll see this with light too, when we talk about light on Wednesday, that this is how you can produce diffraction patterns and interference effects with light. Basically, you take all of the light from multiple sources and you can concentrate them in a single area. So just as a quick example, because we have 15 minutes, we can just calculate. Let's just run through a quick example to figure out where in a room we would have to put speakers. Let me write this out. Where along the x and y axes should speakers go so that we have constructive interference at, say, position 1, 1. Or maybe we make it, yeah, let's make it like 10. No, let's do 1, 1. So we're imagining that we have an infinitely large room. We put 1 speaker here, and we want to know where to put those speakers so that at position 1, 1, we get constructive interference. So here's this is the distance y, this is the distance x, this is speaker 2, speaker 1. So if we want constructive interference, what do we do? Oh, and let's just say that lambda is equal to 2 meters, and v is, I'm trying to come up with this on the spot. Let's do lambda is 3 meters and v is 4 meters per second. So you could work out the frequency from there, but it's not going to be super relevant. And we're going to assume that delta phi is 0, they're turned on at the same time, and delta t is 0 as well. Sorry, they have the same phase and they're turned on at the same time. So constructive interference means the following. It means that delta big phi, the change in total phase at the position 1, 1, has to be equal to 0 or pi, or sorry, 0 or 2 pi, or 4 pi, etc. Right? So there's going to be a lot of places where we can have where we can have constructive interference, but let's try to find a formula for them. So in our case, delta phi is 2 pi delta x over lambda, right? But what's delta x? Delta x is the difference between the distances that travel. So in this case, x2, it's this distance here, and this distance, x1, well, delta x is x2 minus x1. But what is x2? Well, we can use the Pythagorean theorem. It is that distance. It's the corner of a hypotenuse, or corner of a triangle. So it is y minus 1 squared plus 1 squared. So all I did was I just found that this distance is 1 by definition. This distance is y minus 1. And so then I just squared them and took the square root. x1, on the other hand, is square root x minus 1 squared plus 1 squared. And so what we have then is we have that delta phi is equal to 2 pi times square root of y minus 1 squared plus 1 minus square root x minus 1 squared plus 1 divided by, and we're working all meters, divided by 3. And so we want this to be equal to, say, 0. Well, if it's equal to 0, that's easy, because if these two things are the same, then you'll get 0. So if delta phi is 0, that just implies that square root y minus 1 squared plus 1 equals square root x minus 1 squared plus 1. Oh. And that just implies that x equals y. So if we choose that the x-coordinate of speaker 1 and the y-coordinate of speaker 2 are equal, meaning like if x is at position 5, 0, and sorry, if speaker 1 is at position 5, 0, and speaker 2 is at position 0, 5, then we will find that we will get constructive interference. So we'll call 2 at 0x. There are other ways that we could do this. So let's say that if we had wanted, and so that's one possible arrangement of x and y that would give constructive interference. That should be the most obvious, because if like it's symmetric about a line, about the line y equals x. But what if we had chosen delta phi equals 2 pi? Then we would have some work to do. We would have to go and we would have to solve for what y is in terms of x and so on. It'd be a bit of a mess, but it's doable in principle. And so this is one way, or I suppose this is the way, that given a position in space, if you want to place your speaker so you get the loudest sound at that location, you'd have to solve these equations. Now, this is not how that hotel room that I was talking about at the beginning of lecture worked. It was not because there were speakers in various places projecting into a particular location. Instead, what was happening is that there were the roof, or the ceiling rather, of the lobby was a dome. And so hopefully, and we'll cover this in the coming weeks, but domes focus waves, especially when they reflect. And we'll see this with light, but it also happens with sound. And so what actually was happening was all of the waves that were hitting the ceiling were being focused and thus constructively interfering at the center of the dome. So if you stood at the very bottom, or directly below the center of the dome, all of the waves coming from the ceiling, which were bouncing off the rest of the room, were coming down and constructively interfering at me. Because if you treat the points on the dome as, how do I want to phrase this? If you treat the points on the dome as having, as being the sources of sound, they will all have traveled the same distance. And that's why I was hearing what I was hearing. But we'll go into more detail on that once we get into optics, and we'll do this with light instead of sound, because it's a little bit more clear. Right, so I was thinking that I would start, section, or chapter 5 today, but I don't, or lecture 5 today, but I don't think I will, because we're just about out of time, and so instead I'll open it up to questions. So does anyone have questions for me? I haven't written the homework yet, so I can't say for certain. But everything's fair game in the lecture. Oh, let me stop recording.